Thank you very much, Hugo. Thank you very much again, the organizers, for this opportunity. And so, my goal today is complicated. So I think I landed into these things that where I thought I was going to say too little, and now I think I'm going to say too much. So let's see how I handle that. But still, the goal is to talk about the Q&A a little bit. Aaron already talked about the Q&A, and I heard already several people criticizing somewhat the Q&A because, it has a definition which could scare everybody, even the authors of this paper and other paper. But I want to justify a little bit, at least with some evidence, that there is some hope that in the next 5-10 years, there is a very nice theory that explains exactly that the Q&A really can be tested, can be understood, and it's something which is very workable. And it actually goes along the lines of Masato Sushi and Sichuan Shang work, where they do something very similar, but with a different sort of quantitative statement, which is the Dolgopiat condition. And I think it is actually both are part of the very same type of statement and phenomenon, and that's what I want to discuss a little bit now, that it is really some phenomenon that it appears in, like, at least I have seen it appearing in the work of Sushi and Shang, in the work of Asaf Katz, or the work I'm talking about u-Gibbs state. It has appeared in the work we are doing with Martin and Andrei about smooth rigidity, and so I think it worth being studied. So if it appears so much, it really has some reason to exist. But then I want really to start as last time with the most trivial situation, okay? And this already appeared in an Ossoff monograph. In the 60s, so the famous monograph where he proves the ergodicity of geodesic flows on negative curvature. So he analyzed the following situation. You take F from R2 to R2. I'm giving an epsilon digested version of what he did, but it's just epsilon, so he pretty much does the same thing. I'm just cleaning one or two stuff. So you assume f of 0 is 0, so you have a fixed point. It is a hyperbolic fixed point. So 1, 0, it means the same as the 0, 0, so I use it interchangeably. So, and the derivative is already diagonal. Lambda, lambda inverse, let's say lambda smaller than 1. So it is actually, in his situation, he even assumed fully area preserving. It's really at this level that you need it. And there is something called again, normal forms. So, okay, when I say most of normal forms, people tell me that it's just Birkhoff normal form. So it's just a normal form. You call it Moser or Birkhoff, depending on how you like it. But it's just a polynomial game. So you just start killing coefficients of your Taylor expansion of the f in a neighborhood of 0, and you can bring it into a form like this, which is lambda x plus a constant times xy in the first coordinate, and then lambda inverse y minus the constant over the lambda square times xy, and then you have higher order terms. Okay? And this is actually the main reason we call hyperbolic points, okay? Because this form is of the form x times phi of xy, y over phi of xy, and so these preserve the hyperbolas xy equals to constant are preserved, okay? Because if I do this times this, the phi cancel out, and it is preserved. So, which means that the picture is you have these hyperbolas, these hyperbolas, these hyperbolas. And you just, the orbit move along these hyperbolas. So it's exactly the other way around of elliptic points, which also have the same style of normal forms, so a little bit less quadratic terms, where you preserve ellipses. You can make ellipses circles after all, so. And then you discuss how you are moving and how you are rotating along the circles. So then this is the hyperbolic twist, the same way as when you look at the rotation of the circles, you have the elliptic twist. So what is the elliptic twist? Well, typically all the guys are supposed to rotate at the same speed. That's the most standard situation. Well, not most standard, but the basic situation where the line goes to the line. And then the twist map means that you take this line and it goes into something which strict increasing derivative. And so here is exactly the same. You take a line and it will go into something that increase if the c is not 0. And it will go to the line if the c is equal to 0. Okay, and the twisting is fully dominated by this constant c. Okay, you could have c positive, c negative. I think if this c positive is like I said, if c is negative, you go below. And if c is 0, you don't go anywhere. And I was about to say something, and now I forgot. Oh, okay, yeah. I said, just to get into this form, you really write the Taylor of order 3 of the guy. So it just have some coefficients. You conjugate the map with a Taylor of order 3 again, or 2 maybe, and you just start killing equations. You get twisted linear equations that you can solve as soon as, so like, if I want to solve for this x squared, I will have a coefficient of lambda squared, so it's like an eigen problem for lambda squared, so you can solve it because lambda is different from 1. If you want to kill the x, okay, I said x squared, so for x squared I think you get lambda cubed. So when you want to go for x, y, oh boy. Now it's better. So now it has that form. So when you want to kill the xy, then you will get something, I think. So it should be this times this, and if this is in the first coordinate, is this times this divided by this, and 1 over, so it's, for this is lambda. If it is in the second coordinate, it gets with a factor lambda inverse, similar with this guy, so let's do it right. So if this is the first coordinate, you get a lambda squared divided by lambda. If it is in the second coordinate, you get a lambda squared divided by lambda inverse. And there you go. So you essentially get switch whatever monomial here by the corresponding lambda or lambda inverse that appear. This goes in the denominator, and then if you go in the first coordinate, multiply by lambda. If you go in the second, you multiply by lambda squared. Okay, the whole point is that this guy you don't kill, because this guy is a lambda squared times lambda inverse, and then in the numerator you put a lambda, and so you get a 1. And with 1 you cannot solve. So 1 minus 1 is 0, 1 minus any other number is not 0. So you just, it's a beautiful exercise. You really can train your skills by playing this exercise of how to bring into this form. Okay, and it's just at a shed level. It's a linear algebra problem. So I'm not discussing about killing this guy. One can do it sometimes, sometimes don't. So, but let's not get into that. Okay, so then what was Anosov looking for actually? He was studying, okay, I have my Anosov theory, so it's my theory, I call it Anosov because it's mine. No, he didn't call it Anosov, of course, but so he had these very nice, beautiful bundles, and he was wondering, okay, how smooth are these bundles? When you are on surfaces, they are C1 plus Hölder, and the question is, can they be C2? And so he said, okay, let's analyze the local problem. Let's imagine I have this guy, and assume it preserves a C2 foliation tangent or mostly unstable direction. So it's mostly, I think I said lambda smaller than 1. Yeah, so mostly vertical foliation. Okay? So which will be like a C2 germ of unstable foliation, whether it is preserved, but actually when you go to the computation, you can look at the shed level. So it's really about whether you have a shed of a C2 foliation which is invariant at the infinitesimally invariant at this fixed point. Okay, so he just went the computation. I will not do the computation because I have too many things to say, but you can read it or you can, again, do it by yourself. It's really not hard. You just put your vector field here and almost vertical, like a function of the form u of x, and you take the differential of this guy, you write the second order sheds of this function, you look how it maps to the next guy, you just write down the equation and you assume the invariance, and the invariance automatically will tell you, and that's an Ossoff theorem there. So if there is a shed of a C2 foliation invariant under F, then Z equals to 0. Okay, so some extreme variance comes only with the vanishing of this guy. Okay, so this is actually, you can think of this even as a cocycle eventually, but what is important is that you have this C number, which is very detectable, and its vanishing is an abstraction for the smooth of the foliation, and at the same time is telling about how you twist. Okay? So, which means that at the end of the day, you either twist or you get smoothness. So, and luckily, I guess, 60 years later, so this is a win-win situation. So you either have beautiful theory because of this twisting and you can leverage it, and that's to some extent, I think not in this scenario, but in a slightly, or not slightly, but in some other scenarios, you can wait 2 lectures and listen to Masato about these type of things. And in the other case, where C fully vanishes, again, this appears in Masato lecture, but, or Sushi Shang theorem, and in this situation is a paper by Ossoff and Herder, Katok and Herder. That says, if now F from T2 to T2 is area preserving C3, area preserving an Ossoff diffeo, and C of P is 0 for every periodic orbit, P, then F is smoothly conjugated to linear. Okay, so the consistent vanishing of this number means that you are smoothly conjugated to linear. And the linear guys we like, so we have all other type of way of computing these things. So So which means that either you find one point with a twist or you are linear. So that's essentially put you always in a good situation. There is a similar thing that also Martin mentions. I think Martin just mentioned it through his talk. And there is this second situation, which is, again, very similar to this, about anodes of flows, three-dimensional anodes of flows. By Foulon and Hasselblad. Is okay the spelling? That it is now for the flow and is a cocycle pretty much on the same style, but for the time. And it's for volume preserving. Did I say volume preserving? It's for volume preserving. And this describes whether so it is a ecocycle similar to the previous one. Actually, they call it the longitudinal anodes of cocycles. We decided that is a too long name, so we call it the Foulon-Hasselblad cocycle. But it's called longitudinal anodes in the paper because it's like the anodes, but along the longitude, so along the flow direction. And it's some cross derivative between what happened on the stable and what happened with the unstable. And it's exactly at the resonant level, so it is like someone differentiated with respect to the x variable with respect to the y variable. So x here is stable, y here is the unstable. So this produces a multiplication by lambda. This produces multiplication by lambda inverse, and the coordinate you are putting here is the flow coordinate. So this guy gets multiplied by 1 because it's just the flow coordinate. So you get 1 over 1 is 1, and that's always puts you in a cocycle, which is the standard type of cocycle we see about Lipschitz theorem. And so then you can play Lipschitz theorems and vanishing here, vanishing there, or not vanishing. So here vanishing implies ES plus EU is smooth, which implies you are either constant root suspension or contact. So, and again, non-vanishing implies some sort of twist, and the QNI is about twisting, and when you don't have QNI, you are supposed to have vanishing of all this cocycle, which implies rigidity. So, and then as I said, so you either get QNI or some rigidity. So that's the moral of the business. So let me show you one more instance of this. So it's, again, this is still in very baby time, so I think it's reasonably understood in C2 situation, C3 situation, when everything is sort of one-dimensional and life is nice. And my hope is that in the next 10 years, this really will be developed in any dimension, and that's it. So you have answered to all your questions. So the other instance I wanted to comment is a paper by, okay, I need to check the letters. So it's not really about QNI, but it has some things like QNI. So certain integrability part of the game is not so quantitative in some respect, but still. So, okay. Okay, one of the papers we even heard about it, I think, a little bit, is by Alvarez, Sebastian. Next in the line goes Martin. Next in line, I guess, is Obata. And next in line is Santiago. And then there is the second paper that has a lot of authors. Okay, I will not put all the names in this case because these people also are well accomplished. I just put the initial. So It is Avila, Crobissier, Esking, Potrier, Wilkinson, and Shank. Okay? So, yeah, it's hard not to get a good paper with all these people. Okay, what this is about is very in the vein of what is this lecture. So u-Gibbs implies SRB or joint integrability. So that's pretty much what it is. And so the setting is a three-dimensional and also of Diffio with EUU plus EWIQ plus ES. And then you assume a measure which is absolutely continuous along this direction. And then they show that either it's also absolutely continuous along this direction or these two guys jointly integrate. Okay? So there is also previous version by Asaf Katz where he proved this, but assuming some quantitative non-integrability between these two guys, and then from there he showed the extra invariance or the extra absolute continuity. Now, again, the way this is done is different from the QNI, and they don't use explicitly these cocycles, but essentially it is very much related to this type of cocycle forms. And I want to add one very important consequence of the joint integrability here, so that you can really see the rigidity. So already this sort of joint integrability is some sort of rigid situation, but there is the result by Xiao Bogan and Yishi that says that in this case the center Lyapunov exponent, so the weak unstable Lyapunov exponent is constant. So you see that, again, the non-QNI comes with some sort of vanishing of something that implies some rigidity. So, so then how to play more or less this game? Okay, just 2 or 3 observations about how this game is played in this or that situation. So, like you take ES plus EU, okay, and you try to show that it is smooth. Okay, so that's the first thing that should come into mind. So, is this guy smooth or not? Okay, so if it is not smooth, it's because it is, and especially if it is not, the ES is not smooth along the EU, which means that this sum is not smooth along the EU, because the EU part is smooth along itself. So then there should be like a twisting, like what we see in the annals of cocycle games. So someone has to be faster than the other, someone has to be moving at some faster speed. And of course, when you want to accomplish it with Itel, there is these templates that are done by Sushi and Shang, which really allows you to compute this explicitly. So it's like a glorified full-on Hasselhoff-Anosov cocycle, where you still have a finite dimensional cocycle that allows to just understand how this twisting is going. And so if it doesn't vanish, then this exactly explains the non-smoothness, and this, with some hope, implies the QNI condition. If it does vanish, then you get your extra smoothness. Even if you get your extra smoothness, then you can just check the bracket of these two guys, and because in contact, the gas is as smooth as you want, but still are not jointly integrable. But then you can play a bracket. You have a bracket, then it's very easy to test the bracket, whether it's 0 or not. And if it's not 0, you get a separation like crazy. So then you win. So and that's pretty much in general. You have some bundle, any bundle. It could be some sort of sum of guys, and even you can quotient by other guys, so you have to do so. That's why it is 278 pages, so it's to develop some theory about all sorts of operations you can do with bundles. And then you take derivative of this bundle or some coordinates or some quotient of this bundle with respect to this hyperbolic type of, and so on. So R1, R2. And this is a cocycle that is twisted by, well, as we said, so it's the dynamics of over this guy over the dynamics of over these guys. Okay, so if you have resonance of stables versus unstable, like in this lambda inverse, then you will have a standard cocycle which you can do Lipschitz or Kalinin type of thing and analyze reasonably whether it vanishes or not. Otherwise, it's really twisted, and there is no nice established Lipschitz theory when the cocycles are twisted. So there are some theory, but it's harder. So, and that's why one have to really work way harder. But that will really explain you how smooth is this guy versus these guys and establish this business. So let me say two more words about this. So one is paper by, not so bad, Eskin, Potrier, and Shang, where in this situation, they really showed that the QNI that, again, Aaron defined it last time, and I think I will not have time to rewrite it, so I will draw a picture, hopefully soon. But the QNI, again, is about joint integrability of this plus this. And essentially what they show is that non-QNI implies that at every point you have a surface which contains the stable through this point, contains the unstable through this point, and it is tangent at all these points, and not just at the first order, it's tangent at the n level for every n. So actually, there is a discussion whether you fix the n and then find the surface, or you can do it forever, but let's not enter into that. So to the tangent bundle of this, let's say this is unstable, this is stable, so the unstable bundle over the stable of this guy is tangent to every order to the surface, and the same for these guys. So again, it's pretty much what we said about the shed of a C2 foliation being invariant by the dynamics. So here again, you have a shed of a C-infinity foliation tangent to this ES plus EU. But it's only the shed, it's not the germ, so there's not the foliation. It's just the Taylor series satisfies everything to exist, but may not exist. So it's a phenomenon that we also use in the long paper to place center manifolds, where center manifold, when they really come from zero exponents, so you have the whole Taylor series of the center manifold. Okay, you cannot make an invariant center foliation, but you have the Taylor series, you just make it convergent by the typical tricks that every Taylor series is the Taylor series of someone, and you get what we call realized center manifold, and you have absolute no invariance, but when you iterate the difference with the other one you have, it's tangent at infinite order. So as soon as the guys don't get far, you can kill the higher order terms like crazy. So same thing happening here. And that's the thing, and they don't write the other part of the scheme, which is once you have these sheds, you can go and play like an Ossoff and say, okay, then I will have these cocycles arising from this game, and all of them will vanish. Okay? Then, of course, after you get this, you still need to work like an Ossoff-Katok or Foulon-Hasselblad to claim that one of these cocycles vanishes. Then you really get the true foliations and with some smoothness and everything. And once you have the nice smooth solutions and everything, you can try to work like Xiaobo and Yi to get some very nice linear type of game. So that's why I'm saying 10 years, so I'm giving people time to work. So no pressure. Okay, so yeah, I wanted to talk about one more work in progress, so and add one more name to this list, which, let's see, where should I erase? Maybe here. So that also Aaron mentioned it, so this is actually some of these situations, especially in the linear situation, because this is about QNI, there was a constant kappa that actually Bassam asked. So you can have a very strong QNI, which is already kappa equals to 1, so it's just divergence at the linear level. And this will imply some joint integrability at the linear level. Okay, so the further you go with the kappa, so you weaken, you say, okay, any divergence is good enough, then the more sheds you are getting here. So, so this is the work in progress of Rose Elliott Smith, which she's working the linear, probably eventually more, but so far the linear QNI condition implies linear joint integrability. And I hope I can really do correctly my job and show really what the meaning of this linear joint integrability I'm writing here and use it with some entropy argument to show what was remaining in what Aaron said. Okay? Okay, so I think that's good enough about QNI, and now I go to the next step of the talk, which will use this notion of linear joint integrability. Yeah, quantitative non-integrability implies linear joint integrability. It's a triviality, no? Yeah, but the problem is that the quantitative non-integrability is there is some measure here, some measure there, and this guy does this, and this guy do that, and then I need to extract from there some very precise statement, which is some projection along some bundle have to sit in some other bundle, and yeah, then grabbing the points is a mess. So, of course, one could make a more reasonable definition of QNI that will make this implication the typical triviality, but then it will be useless to prove the other theorem. So then it's true that in some respect, and actually this happens in this, all these papers here that were listed here, is like, okay, give me a non-constant function, okay? So it has 1 point of non-zero derivative. That's the most trivial statement you can get. Even a calculus student can prove it. And that's the moral here. So that's essentially everything about this statement. But then the issue is that, okay, it's non-constant, but on a Cantor set. Then it can be infinity flat. And the guy is very non-constant. So, okay. Now, when you work with these guys, the measures are very important. So you test all these integrabilities and this business on set of almost full measures. And so it still could be infinitely flat and the guy moves like crazy. So, but then you want to quantify it. Okay, it's like crazy, but not this amount of like crazy. Okay? And so but then you want still to recover from this very strange situation that, okay, still if you move a little, you have to have non-zero derivative somewhere. And well, that's why the cocycles are there to help you. That at least is my guess. But yeah, no, it's very important, this step. Enough. I can do something else. Okay, so let's go back to, we have an SL2R action on a manifold. And you have this big I, which is this group of upper triangular matrices, and you have a measure mu that is P invariant. Okay, so now you have a, well, plus other hypotheses that will show up soon. Then you have these unstable manifolds. So for this flow direction, so you denote GT, this e to the t, e to the minus t. Sometimes people put an over 2, it's a matter of taste there. So the diagonal group, and you have the unstable manifold for X, and so, okay, notation. These guys are the strong unstables, so it's without the flow direction. And you have stable manifold of points, and you may even have center manifolds, which I will try to avoid them as much as possible, because these are always, so we can still say a lot about when the center, but as always, the statements are nicer when you have hyperbolicity. Okay, so the first observation is that inside here is what we call N, and N is this guy. So it's the orbit of the point by the N group is inside here, and you have the N bar inside here, where N bar is 1s01. The guy always has at least one non-zero, one positive exponent, one negative exponent. Probably larger. Actually, it's not hard to show, and it will be part of the computation I hope to do, to show that if all the other exponents were 0, then this guy is SL2R invariant. And you can think of this as this Lederer invariant principle, but actually the computation I'm going to do is, if you want, is exactly the entropy version of Lederer invariant principle, which is also an entropy statement. So it's really, at the end of the day, all is the same thing. It's just some entropy here equal to some entropy here, and you deduce what it's telling you. So, and that's the computation I want to make eventually. So now I will do what a lot of people hate. Sometimes I myself hate it, but I often do things I hate. So I will start a proof without stating what I'm proving. Okay? And even I will, in the middle of the proof, I will need some hypothesis. And that's the other hypothesis that is appearing here. But just to let you know, so what I want to show, the very first baby step is I want invariance by this direction. Okay, so I want the measure to become SL2R invariant. Okay, and in the meantime, hopefully to show that the measure is actually absolutely continuous along this direction as well, and that it's also absolutely continuous along this direction, the full stable. And then if there is no hyperbolicity, then concludes from there that if there is no center, then concludes from there that the measure is absolutely continuous. And then, well, I get from P invariant to fully absolutely continuous, just with other hypotheses. Okay, so how to do that? So we have this U plus of X. These are subgroups of these guys we call GSR of X. Sometimes one is supposed to put a U on them because you have also a structure on the stable. This is a structure along the unstable. These are these normal forms that we worked so hard to build. And actually, these groups belong to SSR, which is strictly subresonant, which means that you go to identity. You don't just stay bounded. So the big importance is that Aaron mentioned it. So this guy has what they are called unipotent. So they are amenable, so you have naturally invariant things, so the hard measure is bi-invariant and life is nice. So which means that this group already acts on the stable manifold, on the unstable manifold, so this group also acts on the unstable manifold and preserves the conditional measure along this unstable manifold. Okay, and this preservation actually implies that you have the orbit of X under this group, which we denoted by bracket X, and this guy form a partition, so a subpartition of the unstable foliation, and the conditional measure now along this new U plus directions are hard measure on this U plus of X quotient by the stabilizer of X in U plus X. And since this is an action, the orbit of a point is canonically identified with this quotient by the parametrization, and the whole point of this unipotent and all this basic Lie group theory is to say that this guy carries a natural hard measure which comes from the projection of this hard measure into this hard measure. And so you have this identification with the U plus of X, you have hard measure here, you have hard measure here, and the claim is that these two guys are the same guy under this identification. And the proof is just by construction, but even more so. You have, again, Le Drapie-Young, and I think that's a very important statement in Le Drapie-Young, and in relation to all these homogeneous structures and normal forms, is that as soon as the measure is absolutely continuous, it's automatically hard measure, because the Drapie-Young gives you the Radon-Nikodym derivative. And the Radon-Nikodym derivative is some product, infinite product, that is exactly the product that appears when you build your normal forms. So which means that you always get hard measure. So you don't need to make other arguments of this Radon-Nikodym derivative or that one. So it's just an addition to what you get. Okay, so so we know this guy is hard measure. Okay, now I need one more object. So that's the picture along the unstable. Now I need to move to the picture along the stable. So now what happens along the stable? Let's use brackets like in the paper. So along the table I have a conditional measures as well. But now they are nothing, so I have absolutely no invariance under no group here. So I still want some homogeneous guy, okay? And in all this discussion I did before, so you get always the unstable integrating with the full stable. But when you go to higher dimension, you only hope that you will integrate with some piece of the stable, so not with all the stable. So like if you have a product system T2 times T2, and the measure lies in just in one T2, then, well, or you go to nil manifold because in the torus everything is John integrable, but you really need to find who is the companion. And is the measure. The measure is just a Cantor measure or whoever, so we have no clue, but you can build what would be the Zariski closure of this new as X. So what is a Zariski closure? So in general, so I am as ignorant as anyone else. So Zariski, for me, is a beautiful name to say, is the closure that is beautiful. So what does it mean? You just take a polynomial curve that vanishes, or where your guy, so if it is a polynomial curve, it's a polynomial curve where your support of the measure sits inside. Okay? So that's essentially the Zariski closure. And of course, you make it a little bit better because support is like too big. So you just work with invariance and everything, and it's just you take a small ball inside here, you restrict this measure to this small ball, even you take a positive measure set inside of this ball, inside here, and this will sit in some polynomial curve. And this polynomial curve, you take it with minimal dimension, end up being unique, and invariant by the dynamics, because when I say polynomial, I have my stable normal form, which is a bunch of polynomial business, and it's a polynomial structure that is invariant by dynamics, so as soon as I get a polynomial, I get invariance by the dynamics. So I have now my candidate to the counterpart, Ls of x, on the stable, and the hope is that this guy will join integrate with this u plus, whatever it means. Okay? Okay. Let me just make one more comment. So I said that my goal is to show that the measure is invariant by the n minus. So once it is invariant by n minus, I can start to reading the paper again from the beginning, but now switching the stable with the unstable. And then this guy will become the u minus x, so it's, or the orbit of the group u minus x, okay, eventually. Okay, so I need yet another object here, which comes with this non-integrability, but before, not before, I think I'm ready to define this object. I have this d of x, which comes from doing the following. So I need to stabilize a little bit this guy, so I need to retest once again the Q&I condition, essentially. So what I do is I take this tangent space of the Ls at x, okay? But I start moving it along the unipotent n of x. Okay, so they have the stable manifold here, and I start moving it along this n of x. So I want really to move, because if it moves, it's good for the theory. So it gives you the Q&I. So if I'm moving it, then what I'm doing is I take n times x, I take the tangent at this point of this guy, and then I bring it back by the derivative over x. So I just take this Ls of x and x here, and the tangent space, and I bring it into something here. And this may be moving, okay? So I have a bunch of guys, so I take the span of these guys, the linear span. Okay, so this is a vector space, and since this guy is invariant and the n is a nice guy, so this guy is invariant under the geodesic flow, under the GT. Pretty much the goal of doing that is it is n invariant. That's why we move a lot like crazy. So it is P invariant. Okay, so still this is not really the guy I want. I want to play the same game along the n bar direction. Now I will tell you why I cannot do it, but how you just get rid of things you cannot do. So my measure is not invariant a priori along the n-bar direction, which means that most likely the condition along the n-bar, if it is not invariant, are just atomics, which means that if I try to take the point n-bar x, which is moving along this n-bar direction, this point does not exist for the measure. Okay? So all the structure I have is for almost every point with respect to the measure. So if this point is not good for the measure, there is no stable, no unstable, there is nothing. So I cannot really play the same game moving n-bar. So you don't do it. You just take this c-bar of x and you add essentially the Lie algebra of the n-bar over x. Okay, so just this vector space. You want to add this direction, okay, because you want this guy really to contain the tangent to SL2. Okay, so it's not SL2 invariant, it's only P invariant. It's still P invariant because here you are not doing anything. So, but it's tangent to the SL2. So this is the nonlinear joint integrability. So I have my projection pi cs from the tangent of M into the unstable of X, which is just remove the center stable direction of a vector. So the kernel of this pi cs is the stable space, the center stable space. And so this implies, and so, okay, there should be a none here. Linear non-QNI condition. So the failure of the QNI is there. Is the joint integrability, so, or maybe better. None, this implies the QNI. But in any event, the linear joint integrability implies that when you project this z prime of x, it lands into the tangent to the u plus of x at x. So that you cannot get out from there. Okay, and that's what Aaron was drawing last time. And let me write down this drawing again. I hope I can. You have x. Here is u plus of x inside the unstable. You move along the stable here to sign point y. Then you have the u plus of y up here. You take the plane over this guy, which is the unstable, so it's a two-dimensional unstable in this picture, a one-dimensional stable. You take now this point, you take the center stable through this point, and it gives you a point z. Okay? And the quantitative non-integrability is about how far this point is from this curve. Okay? And so what this row statement tells you is that if you don't have linear divergence, is because this z prime does not separate. And what is the z prime? It's just telling me I move along the LS, I move the LS along this direction, I try to succeed. That's the z prime. Well, the z is how much I succeed. The n is just an artifact of the proof, the n bar. And so then if it's not contained here, I get the z with it linearly outside of the place, and then I didn't stop in my quest, and I can find the greater u plus, and I try again. So when I cannot anymore, row statement tells us I get this. Okay, that's really what I needed. So, and that's how it's used, the QNI, and that's the good thing of testing it this way. So I didn't need to assume any QNI. I did not assume any QNI. The other hypothesis will tell us something different. So I have a my SL2 action, and I just got this property. No other hypothesis. Okay, so I need now to play entropy. Again, this entropy trick, you can think of the Lagrange invariance principle. It also appears in a paper by Margulis and Tomanov, and it appears in a lot of other places. It's a very nice and cool statement. You will see computation very similar to the ones that Jerome and Ali were doing in their lectures. If I succeed. Okay, so let's compute the entropy of the time one map of the geodesic flow. Okay, so let's do some bounds. So this will have some natural lower bound, which again comes from Lagrangian formulas in the way that Jerome were describing, which appear in our paper with Aaron and Sheeran, which says that this is a sum with all the Lyapunov of exponents which are positive of lambda I times the dimension of the associated space intersected with the tangent to the u plus orbit. Because I know that here I'm on being homogeneous, so the measure is hard measure along here, so we see that each of these guys contribute with full dimension into the Lagrangian formula. Then there may be other guys, so in the Lagrangian formula, that's why it's just a priori an inequality. I'm not adding the guys I don't know are full dimensional, I'm only adding the guys that I know are full dimensional. That's part one. Then comes the second part. Compute the entropy for the past. Okay, so this is smaller than equal, and this is just some sort of Ruel inequality, but it's Ruel inequality knowing that the stable support is inside this LS, so I don't need to go beyond to sum all exponents. I only need to sum the exponents on the support of my measure. Okay? So I get sum minus lambda I times dimension of this E lambda I intersected with the LS of x. Okay, because of the tangent at x of this LS of x, to be more precise. Now this guy I can keep going and is inside this z of x. And even inside the z prime, so I can just swap it with the z prime. I have this nice bound. Yeah, I think we are good. Okay, now comes this condition here. So this tells me that when I do z prime x intersection the tangent to u plus x, this contains, actually it's equal pretty much, but I only need the containment, the tangent to u plus, so I don't get anyone else. Okay? Not with u plus, I'm sorry, because this is really trivial. When I intersect with the unstable space, now it's better. So I just get, well, it's the same thing after all. I just follow from this business. You intersect with the unstable both sides, and you get this statement. And this you can even go and intersect just with the tangent to the u plus. So all this is to claim that this is larger than or equal to the sum lambda I positive of lambda I dimension of E lambda I intersection the z prime of x. Okay, now finally, I put both things together and I get, let's see if I succeed, HG1 minus HG inverse is larger than or equal the sum over all possible exponents of lambda I times dimension of E lambda I intersected C prime, and this is nothing but the integral of the log of the Jacobian of G1 restricted to the C prime guy, d mu. Okay, so I get this, and this is 0 because this is entropy minus entropy, so that's 0. And this gives you this beautiful formula, which essentially shouldn't surprise much. So it's just you work hard to prove something that it is very natural, because this is some sort of SRB measures. And the whole point of SRB measure is that they dissipate volume. So the integral of log of Jacobian for an SRB measure is supposed to be negative unless you have some conservation. So, and that's exactly what you are getting here. The integral of log of Jacobian should be negative unless it is equal to 0. And equal to 0 means some conservation. Okay, and here comes the other hypothesis, which is the one that Aaron mentioned, which is if E is a p-invariant bundle, then the integral of log of the Jacobian, of G1 on E is larger than or equal to 0. So that's the condition, and this condition that is testable, is essentially an open condition, and you can really play with it. Okay, so it's less than or equal to 0, it's larger than or equal to 0, it is 0. Okay, so I get this is larger than or equal to 0, and I get this is 0, I get equality here, I get equality in all the inequalities I put, I get equality. Okay? In particular, I get the n bar guy coming from this guy. So I get the dimension is 1 in this contribution, because that's why I put the n bar on purpose in this game. So I get a 1 contribution from the n bar, so I get the invariance. So the guy is bi-invariant. Now I reverse the game. I use again the formula, and all these are integer dimensions, which again, Ledrapie-Young tells me that then the measure is absolutely continuous along this LS. So I get the absolute continuity, I get everything, and then you can still move a little bit further, and actually the other condition was a little bit stronger than this, was that this integral is positive unless E is top dimensional. So that really is the strongest version of the other condition, in which case you get that the tangent to L, so the C prime essentially has to be everything, because otherwise this should be strictly positive, and I know it's 0. So then I get the C prime is everything, and from there you get that the measure is continuous along stables and along unstable, so it is absolutely continuous. Okay, I should stop here. Thank you.
No. I just want to know, is there any example for your second situation? For the SL2R action, except the geodesic flow of the surface negative coefficient, except this one.
Yeah. Okay, this actually. So there is the paper of Eskin and Mirzakani, where they do this for Teichmüller flow, and one of the purposes of this work was to do this in the product of Teichmüller flows.
Okay.
So, and this is the addition in this situation. Of course, then it's not used exactly, so it is used something like I did, but not this other condition. So this part of the argument is the same, but then you have to use other condition, because these guys are symplectic and you have to understand a little bit more. And in this case, you actually show that this linear joint integrability is actually joint integrability, and you get, seriously, the measure sits in a submanifold inside your space. So, and that actually is the big conjecture, is that, forget a little bit about this other hypothesis, which is just to get something interesting, is that this failure of QNI, which implies some infinitesimal joint integrability, actually should imply a truly joint integrability, and the measure should sit, well, hopefully in a manifold, there are counterexamples, which is this three-dimensional and also flow, diffeos, where there still is a foliation which is Joule integrable, and the measure is Lebesgue along this subfoliation. So the conditional measures are Lebesgue along these subfoliations.
Thank you. More questions, comments? So let's thank Federico again.